There you go.
Thank you. Good morning again. Uh, we have three more types of refractories to finish up basic refractories: the chrome magnesite, the phosphorite, and the spinel. So again, it's always the same format. We'll look at the raw materials, the phase diagrams, how these materials are made very briefly, what the microstructure looks like, and a couple of the important properties. So chromite is the mineral. It's FeOCr2O3. This is a pure spinel structure. But chrome ore is really a solid solution of 6 different spinels. So again, a spinel is an RO, R2O3. So this R here is the +2 ion. This is a +3 ion. So these are the R2O3 groups. These are the RO groups. So for R2O3, we have Cr2O3, Al2O3, and Fe2O3. And these are the percentages, 40, 55, and 5 that you usually see in a chromite ore. And then for the RO groups, it's FeO and MgO. And these are the percentages that you would usually see in this raw material. So if we look at FeO, we can have an FeO Cr2O3 spinel, an FeO Al2O3 spinel, and then an FeO Fe2O3 spinel. And for MgO, we have the MgO Cr2O3 spinel, the MgO Al2O3 spinel, and finally the MgO Fe2O3 spinel. So chrome ore is a solid solution of 6 different spinels. But chrome ore also contains quite a few impurities. So these are the major impurities: serpentine, which is a hydrated magnesium silicate, 3MgO, 2SiO2, 2H2O, and clinochlor is 5MgFeO. So these are substituting for each other: Mg and Fe. Al2O3, 3SiO2, and then 4H2O. And then the feldspar, this is a calcium-based feldspar, CaO, Al2O3, 2SiO2. So these are minerals that are commonly found in chrome ore. Plus, there's a lot of low-melting glassy silicates. So with all of these impurities, chrome ore doesn't have a distinct melting point because of all the glassy phases present. Glass doesn't have a distinct melting point. It just softens as you increase the temperature. So it basically has a melting range, and it just depends on what spinels are present, how many silicate phases are present, what's their melting range. And it turns out that these silicate phases may melt at pretty low temperatures, 12, 60 degrees C. So all of these impurities and silicates create issues for chrome ore material. So there's basically 2 components in this material. You can think of it as a composite. You have the spinel grains and this gangue silicate that is basically the matrix. So the silicate bonds the spinel grains together. It fills cracks and voids. And we're usually looking at some type of magnesium silicate as this glassy bonding type phase. So here are 3 different chrome ores, one from South Africa, one from Japan, and one from the Philippines. And you can see the chrome content. This one's pretty high, 47%. These two are around 30 and 33%. So chrome is less than the Cr2O3, the chrome oxide is less than 50% of this material. MgO is another major component. FeO, Fe2O3, Al2O3, and an SiO2. So they're all present. And this one shows a small amount of lime, CaO. So it's a pretty complex raw material. Again, it's less than 50% CR203, and you got MgO, FeO, Fe2O3, Al2O3, and SiO2 present. Here's another example of an enriched chrome ore. So this one is enriched with MgO, and I'll go over why that's done in a few minutes. This is one from England, that's a sintered product. This is one from either Canada or US, that's a fused product. So you can see the MgO content is about 60% here. In these, this was about 11, 20, and 17. So these are enriched substantially in MgO. The chrome contents are down to about 18%. Here we have Fe2O3 and Al2O3 are still the major other fairly significant or major components. SiO2 and CaO are here in lesser quantities. So this one's enriched with MgO. So what happens when you apply heat, increase the temperature? So we can look at oxidizing and reducing atmosphere. So in an oxidizing atmosphere, I mentioned that we can have Fe2O3 and FeO present in these materials. So Fe2O3, when that's present, it's going to be in a spinel. It's unaffected. This is stable in an oxidizing atmosphere. But the FeO that's present in the spinel oxidizes to Fe2O3. So now this RO content, FeO is an RO. So the RO content decreases and the R2O3 content increases. So we oxidize FeO to Fe2O3, the RO content decreases, the R2O3 content increases. So in the spinel, the RO and R2O3 become unbalanced and two other phases appear. So this spinel, MgO, R2O3, where R2O3 can be these three components, Fe2O3, Cr2O3, Al2O3, but we're really enriching this Fe2O3 content by oxidizing the FeO to Fe2O3. So you're creating a spinel by reacting with the MgO. And then the solid solution excess, this R2O3, which is going to primarily be Fe2O3, creates or precipitates needle-like inclusions in the chrome grains. So when these inclusions form, there's a volume expansion and they can actually disintegrate the chrome grains. So we're forming more spinel because we have excess MgO in a useful chrome-based refractory material, and we're forming these inclusions. So this is a photograph of a microstructure of a chrome grain, and we're forming these precipitates. This one is CrFe2O3, but it's going to be high in Fe content. So these white needle-like inclusions are these precipitates, and if you have enough of them present, there's a volume expansion and it will disrupt the structure of the chrome grains. If the atmosphere is reducing, the FeO is stable. So FeO in the spinel is unaffected, it's stable. And then the Fe2O3 is reduced. So the Fe2O3 in the spinel is reduced to FeO. So if a chrome ore contains Fe2O3, or if the chrome ore has been oxidized, and you form Fe2O3, you're going to reduce this Fe2O3 to FeO. That involves a volume expansion and cracking. So one of the problems with the chrome magnesite refractories is repeated oxidation reduction cycles causes this cracking due to the change in oxidation state between FeO and Fe2O3. So the iron oxide content should be less than 18% to prevent this kind of cracking from these oxidation reduction cycles. So to make a chrome ore usable refractory, you have to add MgO. So when you add MgO, it reacts with the silicates and it forms phosphorite. So that's 2-MgO-SiO2, that's the magnesium silicate. It has a melting point of 1900 degrees C. So you add MgO, it reacts with the low melting silicates, removes them, and forms a higher temperature compound, phosphorite. The MgO also balances the R2O3 spinel. So I just showed that as Fe2O3 oxidizes, as FeO oxidizes to Fe2O3, the MgO that you add reacts with this Fe2O3 to form a spinel. So MgO enters the spinel to replace the FeO. It reacts with the newly formed Fe2O3 and maintains the spinel structure, MgO Fe2O3. So the addition of MgO removes the low melting silicates and reacts with the Fe2O3 to make spinels. But these spinels are going to be higher temperature versions. So the MgO stabilizes the spinel structure in an oxidizing atmosphere. It increases the melting range because the spinels that form with MgO as the RO group and R2O3 groups have higher melting points than spinels with FeO and R2O3. So here's MgO plus Cr2O3, MgO plus Al2O3, and MgO plus Fe2O3. So this is the MgCr2O3 spinel that melts at 2180 degrees C. This is the MgAl2O3 spinel. It melts at 2135 degrees C. And then this one is the lowest melting one, MgFe2O3. It melts at 1713 degrees C. Still a pretty high temperature. So any of these three spinels can form when you add MgO. They're all high melting. And again, the MgO removes the low melting silicates. So these are the 6 spinels that I mentioned and their melting points. So FeO, Cr2O3, that one, they didn't really show a melting point here because of this oxidation reduction issue. So they're looking at a decomposition of FeO, Cr2O3 because of FeO oxidizes to Fe2O3. But this spinel MgCr2O3 is 2180 degrees C. FeOAl2O3 is 1780 degrees C. This is actually spinel. It is a mineral spinel, which we'll talk about later today. MgOAl2O3 is 2135. But this spinel, FeO Fe2O3, is only 1594. And the MgO Fe2O3 is a little bit higher, 1713. So this spinel with FeO is low melting. This spinel with FeO and going through the oxidation reduction causes those issues with the volume expansions and contractions. So when you make a chrome magnesite refractory, if chrome is the major component, if it's greater than 50%, it's called a chrome magnesite refractory. If the magnesite is the major component greater than 50%, it's a magnesite chrome refractory. So we start out with chrome ore and we add MgO. We enrich it with MgO. This is the dead burned MgO, which we talked about. And usual processing of crushing these materials, screening them, and mixing them in the right particle size distributions. Dry pressing, again, is a small water content. It may be an organic binder added. Drying and then firing. So the firing can be as low as 1400 degrees C or as high as 1800 degrees C. So a low firing cycle in a range of 1400 degrees C is known as a conventional bonded material. If it's fired at a high temperature, it's a direct bonded material. So conventional bonding versus direct bonding. Conventional bonding is centered at low temperatures, and you end up with coarse and fine spinels, the chromite spinels and MgO grains. They're going to be separated by this phase phosphorite to MgO-SiO2. You're going to have some monocellite present. We talked about that material, CaO, MgO-SiO2, and low melting silicates. And the silicate phase is going to control the high temperature properties like creep and hot strength. So this one is conventional bonding is firing at a low temperature and relatively high impurity content. Direct bonding is centered at higher temperatures, and you're going to have more pure materials. So you're going to have coarse and fine chromite spinels and MgO grains, and now they're going to be in direct contact, and the silicate phases and other phases like phosphorite are going to be isolated because they're going to be also lower amount. So direct bonding centering at high temperatures and lower impurity levels. So now you have crystals in contact with each other. That's direct bonding, and that's going to control high temperature strength and deformation behavior. It's going to increase the strength and increase the creep resistance. So this is a microstructure. This large white region here is a chrome grain. There's another chrome grain here and over here. And then these rounded crystals are MgO. And then the gray area is the silicate matrix. So this is a conventional bonded material. You can see the great deal of the matrix material separating the MgO crystals and the chrome grains. This one is more of a direct bonded material. Here's a chrome grain. Here's some more chrome grains in this area here, smaller crystals. And then these grains are the MgO, this gray area with the white precipitates. That's your MgO Fe2O3 precipitate within these MgO grains. There's a little bit of isolated silicates present over here. These are regions are pores. They're just filled with the resin to make the polished section. You can see a lot more of the MgO grains are in contact with each other. They're in contact with the chrome grains. Chrome grains are in contact with each other. So there's more direct bonding here and isolated silicate phases. So this is a material that I examined. This is a 25X SEM photograph. This material is 45% MgO and about 27% CR2O3. You also have Fe2O3 at about 14%, Al2O3 about 12%, and some lime and also silica. The dark regions here are the pores. And then if you do the chemistry of the different grains, these type of grains, a little bit lighter than the MgO grains. These are the chrome grains. You can see there's quite a few scattered throughout the microstructure. The chrome is about 52% CR2O3, 18%, 18 or 19% Fe2O3, about 15% MgO, and about 13% alumina with a little bit of silica. These are typical chemistries for the chrome grains. And here's a MgO grain of about 90% MgO, and the primary impurity is Fe2O3, about 7%. There's also some alumina, silica, and lime present. And if you go to a higher magnification, this is 200X, you can see the chrome grains quite clearly. You can see the MgO crystals, you can see the grain boundaries, and then you can see this MgO Fe2O3 precipitate, these white regions within the MgO grain. This gray colored area, a little bit darker than the chrome grain, is a silicate phase. There's a little more isolated silicate phase here and so on. So if you map the elements, this is CR in this orange color. You can clearly see the two large chrome grains and then some smaller chrome grains. The orange is the Mg. You can see the little black spots within the MgO grains. That's the precipitate. Aluminum is in blue here. It's primarily concentrated in the chrome grains. You can easily make out, again, the two coarser chrome grains and some smaller ones. Iron is pretty evenly distributed, so it is kind of a blue turquoise color. You can see it's in the MgO grains where it forms the precipitates, and it's also in the chrome grains. And then the green here is where the silicon is located. So that's your silicates, your low melting or lower melting silicates. And you can see in this material, they're pretty isolated. You can easily see where they're located. So for properties, the deformation under load or creep resistance, it's really going to be determined about how many impurities you have, especially the silicate phases. So if it's conventionally melted, conventionally formed or fired, it's going to have a lot more impurities present. These low temperature silicates are going to decrease the creep resistance. But if you have a direct bonded material, you're going to have good creep resistance and good high temperature strength. The thermal shock resistance is reasonable because chrome additions to MgO decrease the thermal expansion. Again, MgO is high expansion, poor thermal shock resistance, but the chrome additions lower the thermal expansion. And corrosion resistance. Iron oxide dissolves in these chromite spinels, gives rise to a volume expansion, which causes disintegrations. And you have to add MgO to improve the corrosion resistance. One of the problems with the chrome ore is hexavalent chromium, Cr+6. That causes cancer. So the use of chrome-based refractories, I guess, has been declining, and they're actually replaced with the MgO-Al2O3 spinel type materials. So here's some possible reactions. CaO and Al2O3, which is the calcium aluminate cement, can react with Cr2O3 plus oxygen to form this compound right here, CaCrO4, and I put it Cr in red because it'll be a +6 hexavalent chromium. CaSiO2 plus Cr2O3 forms the same compound, CaCrO4. There's some other byproducts here, CaO, Al2O3 and CaOSiO2. And then this spinel MgCr2O4 plus lime plus oxygen forms the same compound, CaCrO4 plus some additional MgO. So this compound, CaCrO4 over here, when it reacts with water, it becomes water soluble. So that's an issue. So you end up with CaCrO4, 2H2O. So the formation of this hexavalent chromium is a safety issue. These are three refractory compositions. They're all enriched with MgO. So it's a 50, 60, and 80% MgO material. The densities in pounds per cubic foot are pretty high, around 200. These are all around 16, 17% porosity, which is typical. The cold MOR is reasonable. These three do not have terribly high hot MORs. This is pretty high temperature, 2,700 degrees F, 500, 350. These are pretty decent, but this one's only at 160. The MgO contents, 50, 60, and 77. And then the balance is Cr2O3, Fe2O3, alumina. And you can see as you go up to the higher MgO contents, these impurities decrease, SiO2 and then CaO. So the next group, phosphorite refractories, and we'll do the same sequence. The raw materials, the phase diagrams, processing, microstructure, and properties. So there's a question here about alumina refractories. So carrier plates, I'm assuming that's a slide gate, a material. I'm assuming that's that. I teach a course on properties, and one of the properties is thermal shock. So the particle size is real important when we talk about thermal shock resistance because of the nature of the fracture path. Generally, coarser particles have higher, dissipate more energy during a thermal shock. So coarser particle size distributions tend to do better in thermal shock. If it's a slide gate material, that may be an important factor. If it's not a slide gate material, let me know. But the size distribution is important in an application like a slide gate where obviously it's thermal shocked. So the size distribution would be important. So phosphorite is 2-MgO SiO2. It's in MgO refractories. It's in the chromagnesite refractories. It's a high melting point, 1890 degrees C, and it's about 57% MgO and 43% SiO2. The raw material is olivine. So olivine happens to be a solid solution of phosphorite plus another mineral, phthalate, which is 2FeO SiO2. The problem with phthalate, its melting point is only 1205 degrees C, and olivine is about 15% phthalate. So the presence of phthalate allows large amounts of liquid to develop at these lower temperatures. Also in olivine, there's other minerals present, serpentine and talc. They're magnesium silicates that are hydrated. So serpentine is 3-MgO, 2SiO2, 2H2O, and talc is 3-MgO, 4SiO2, 2H2O. These are not high melting point refractories. So this is what the phase diagram looks like for olivine. It's a solid solution of phosphorite, which is 2-MgO SiO2, and phthalate, 2FeO SiO2. So it forms a complete solid solution. So here's 100% phosphorite. Here's 100% phthalate. So phosphorite melts at 8 about 1890 degrees C, and phthalate 1205 degrees C. So you can see the solidus curve here. So everything below the solidus curve is solid, but you can see how rapidly the use temperature drops as you add phthalate to phosphorite. So it looks like, well, maybe 30% phthalate drops you down to about 1600 degrees C. So here's some raw materials, one from Russia, one from Norway, and one from North Carolina. They're about 40% silica, 47% MgO. And then the phthalate is the source of Fe2O3. This one's about 12. These two are about 7. And these have a little bit of alumina also. So in the MgO-SiO2 phase diagram, this material, serpentine, at 1559 degrees C, we'll show that on the phase diagram. It's still about 60% phosphorite, but it's almost 40% liquid. And then talc at 1544 degrees C is only about 4% cristobalite and almost 96% liquid. So these two materials are very undesirable. So here's the MgO SiO2 phase diagram. This is 100% MgO. This is 100% SiO2. And right here, this vertical line is 2-MgO SiO2. That's phosphorite. So to the left of this line at the higher MgO contents, you're in the phase field MgO, periclase, and phosphorite. And you can see 1850 degrees C is where liquid forms, above 1850 degrees C. So anywhere in this phase composition, roughly 60%, higher than 60% MgO, you're going to be in the area of periclase of phosphorite, and it's a high temperature material. The liquid doesn't form until 1850 degrees C. Serpentine would be in this area, talc would be in this area. So at high temperature, the phases that are present are phosphorite and what's known as clinoansitite. Clinoansitite is MgO SiO2. It's right over here. I don't know why it's not shown on here, but it's a 1-to-1 ratio. But if you're to the right and you have impurities like serpentine, 1557 is where the first liquid appears. So you have phosphorite and liquid. And if you're over here, you have clinoansitite and cristobalite. And as you go up in temperature, 1543 is where the first liquid forms. So materials like serpentine and talc are going to put you in this part of the phase diagram. So refractories, I mentioned, are not always at equilibrium. The chemistry is not uniform. So silica plus related impurities tend to be concentrated at grain boundaries. So the local composition is not the same as the average composition. So the grain boundaries or the matrix may be totally different than the coarser grains. So the formation of clinoansitite is possible in phosphorite refractories if the impurities are going to be concentrated at the grain boundaries. So when these low melting phases form like clinoansitite, which melts at 1557 degrees C, you're going to have a low strength at high temperatures, and you're going to have poor creep resistance. So when you manufacture a phosphorite refractory, the melting rate increases rapidly as the SiO2 content increases beyond phosphorite. So if you're on the right-hand side of that phase diagram, that's undesirable. And the liquid falls to 1557 as the SiO2 content increases beyond phosphorite. So as soon as you you go to the right of the phosphorite composition, you're in a situation where you form liquids and large amounts of liquid at very low temperatures. So the exact same situation exists as for a chrome magnesite refractory. If you want to make a usable phosphorite refractory, you have to add MgO. So no suitable refractories can be manufactured with SiO2 contents beyond that needed to form phosphorite. So all your phosphorite refractories have to be in this region to the left of phosphorite. If you're to the right, you don't really, you're not going to make high temperature refractories there. And you're going to end up with clinoansitite, plus a great deal of liquid at high temperature. So phosphorite refractories have to be in this phase field. Phthalate is a source of iron oxide, FeO, so that can form a great deal of liquid at 1450 degrees C. So this is the MgO, FeO, SiO2 ternary phase diagram. So on this binary SiO2, MgO, here's phosphorite, here's ansitite, clinoansitite. And then this is the FeO, SiO2 phase diagram, the binary. And over here you have two FeO, SiO2, that's phthalate. So when you connect phosphorite and phthalate with this tie line is cross-hatched here, that just indicates it's a solid solution. But as you go from left to right, from phosphorite to phthalate, and you look at the temperature contours, it's 1800, 1600, 1400, and then 1200. So you can see how phthalate really lowers the use temperature because of the FeO that's present. So additions of MgO to olivine, it converts these other minerals like serpentine and talc to phosphorite. So it makes a high temperature material. And it also combines with phthalate to form this magnesiopherrite, MgO Fe2O3. And that has a melting point of about, we've mentioned it before, 1713 degrees C. So MgO forms this spinel, which is pretty high melting, plus additional phosphorite. So also under oxidizing conditions, the FeO is oxidized to Fe2O3. That was the FeO in phthalate. It becomes Fe2O3 under oxidizing conditions. And then the SiO2 is liberated. So the MgO can react with Fe2O3 to form magnesiopherrite, and also it can react with the silica to form the phosphorite. So you have to add MgO to olivine. So when you process this, you start out with phosphorite or olivine. You have to add dead burned MgO. And again, it's crushing, screening, and mixing, followed by usually a dry pressing operation. And they're fired in this range, 1400 to 1800 degrees C. So these are going to be what is known as the conventional bonding type materials. So you can have primarily phosphorite, small amounts of MgO, and the magnesiopherrite, but you're still going to have a reasonable amount of the silicate phases, which is going to control the high temperature deformation. So these are conventional bonded, so they're still going to have a considerable silicate phase present, which hurts the high temperature properties. So some of the key properties, deformation under load is usually going to be poor because of the silicate phases present. This material has really good slag resistance, especially when you have iron oxides present, because it can tolerate a reasonable amount of iron oxide. And the thermal shock resistance is poor because of high thermal expansion. So every time we look at these properties, there's always a contrast there. You never seem to have every property that you desire to be excellent. So these are really good in slag resistance, but poor hot strength and creep resistance and poor thermal shock resistance. There's always a trade-off on these properties. So these are enriched with MgO 55%, 60, and 65%. The densities are around 140, 145. This is about 130 pounds per cubic foot. So these are processed at pretty high porosities, maybe 25 to, this is 37%. And the cold crushing strengths are still pretty reasonable. The RUL, the resistance under load. So these are samples that are heated under 25 PSI. And as soon as they reach 5% deformation, they're heated at a load of 25 PSI. And as soon as they reach 5% deformation, these temperatures are recorded. You can see they're not very high. This one's about 1300. This is about 1500. This is a little higher, 1560. So the RUL really defines the upper use limit. So you're heating up the material and it's deforming significantly at these temperatures. So at that point, it has poor creep resistance and low hot strength. The MgO contents have to correspond to their level of MgO, and the primary secondary component is silica. There's the iron oxide present also from the phthalate. So that's the phosphorite materials. And then spinel refractories, again, raw materials, phase diagrams, processing, microstructure, and properties. These spinel refractories are based on MgO and alumina. It has the spinel crystal, but it's actually the spinel mineral. These are replacing the spinels that have the chrome oxide in them because they're safe. They're not carcinogenic when you form the +6 chrome. So spinel has a melting point of 2105 degrees C. It's about 28% MgO and 71% Al2O3. It's a man-made material, so it's synthetic. It's produced from a mixture of alumina and magnesia. And there's a sintered version and a fused version. So when you sinter it, you take the powder that's calcined, you form it into briquettes or pellets. You sinter it at a high temperature, 1800 degrees C, and then you crush and slice that product. If it's a fused material, you have to melt it at a temperature higher than 2105. So it's usually melted at 2200 degrees C. It's poured into an ingot, and then it's allowed to cool, and it crystallizes upon cooling. And it's going to form large, dense spinel crystals. So simply MgO plus Al2O3 forms this stoichiometric spinel, MgAl2O4. So for a flow diagram for sintered spinel, you start out with a calcined alumina and a calcined magnesia. They're milled, perhaps in a ball mill, to get into a mixture. They're granulated or pelletized. They're dried and sintered, and those pellets are crushed. They may go through a purification step, and then the final product is screened into different sizes. And the fused material, again, you're starting out with a calcined alumina or a calcined magnesia. You fuse these, and then you pour them into an ingot. After they crystallize, they're crushed. You might have a purification step, and they're again screened into different sizes for the final product. The advantage of a fused material is it's going to be large crystal size and low porosity. So it's going to have better corrosion resistance than a sintered material. So stoichiometric spinel is MgO Al2O3. But there's a range of products that you can make. You can have an MgO-rich material, which you're going to end up with periclase and spinel, or you can have an alumina-rich material, you'll end up with corundum and spinel. So this is what the MgO Al2O3 phase diagram looks like. This side is 100% MgO. This side is 100% Al2O3. Here's where stoichiometric spinel is. It's a little higher than 70% alumina. And you can see there's a solid solution right here. So at this point here, you have a solid solution that has 61% Al2O3 and the temperature is 2050 degrees C. At this point here, you have a solid solution that extends to about 93% alumina, and this is 1925 degrees C. And you can see as you decrease the temperature, this amount of solid solution is also decreasing. So a curve between two solids is a solvus curve. So if you extrapolate these solvus curves, this is between MgO and spinel over here. So this is a two-phase field, this is a single-phase field, and this is spinel plus alumina. So both of these solvus curves, if you extrapolate them to low temperatures, they're going to meet and form stoichiometric spinel. So the MgO dissolves about 70% alumina at 2050 degrees C. So this is a solid solution region. And then dropping the temperature to 1650 degrees C, MgO doesn't really dissolve in alumina. So 0%. And then on this side of the phase diagram, the solubility of MgO in alumina is only very small parts per million. So spinel is a solid solution here. There's some solid solubility here. So a little bit of alumina can dissolve in the MgO. And on this side of the phase diagram, there's no solid solutions. So I put this red line in here. That's stoichiometric spinel. So if you have an alumina-rich spinel, you're going to be in this part of the phase field. If you have an MgO-rich spinel, you're going to be in this part of the phase field. So you can see this is to the left of stoichiometric spinel, so it has to be MgO-rich. And then this phase field is to the right of stoichiometric spinel, so it has to be alumina-rich. And this is another version of the phase diagram. It's only the left-hand side. So 100% MgO up to spinel. So it's just this part of the phase diagram up to this red line here, but it's going to a lower temperature. So you can see how this line converges at the spinel composition. So if you extrapolate the solvus curves, so at low temperatures, you can see you now have stoichiometric spinel. So depending on how you process this material, how fast you cool this material, if you cool it quickly, you're going to end up with these alumina-rich or MgO-rich spinels if you're off stoichiometry. If you cool it very slowly, it'll probably go back to stoichiometry if you're at the right composition. So spinel is man-made. You start out with MgO, Al2O3, same processing, crushing, screening, mixing, dry pressing, drying, and firing. And the spinels are fired from 1400 to 1800 degrees C. You can also make an MgO-rich spinel. So if you add MgO to spinel, it will be MgO-rich. Again, it's the same crushing, screening, mixing, dry pressing, and then firing at 1400 to 1800 degrees C. So, so this one is just spinel. This one is enriched with MgO. And basically, this is kind of a composite material. You're going to have coarse MgO aggregates and then finer spinel crystals for the matrix. So this is going to be coarse MgO aggregates surrounded by a spinel matrix. So the magnesia-rich spinels are about 28 to 48% MgO. The alumina-rich spinels are about 7 to 28% MgO. So if you have a magnesia-rich spinel, the magnesia crystals precipitate from the magnesia-rich spinel. And if you have an alumina-rich spinel, the alumina crystals precipitate from the alumina-rich spinel. So these are these two regions right here. This is magnesia-rich, and this is alumina-rich. So those are the compositions. Magnesia-rich is 28 to 40 weight percent. So that's about in this region here. And then 7 to 28% MgO is going to be in this region here. So that's alumina rich and that's MgO rich. So depending on how you cool these, it's going to control how the precipitation takes place, how much magnesia or alumina crystals precipitate, and their size. And then the second thing I mentioned was the magnesia aggregates in the spinel matrix. So that's the spinel bonded magnesia. So the spinel crystals are direct bonded to the magnesia aggregates. So you have MgO aggregates in the spinel matrix. That spinel matrix can either be magnesia rich or alumina rich, or it could be stoichiometric spinel. So there's a lot of flexibility in these compositions and how you put these refractories together. These generally have pretty good thermal shock resistance, good hot strength and creep resistance, but their slag resistance is basically average. So these are sort of the key properties. For most refractories, they have to have thermal shock resistance, corrosion resistance, and high strength. So these are some spinels with different MgO contents, 30, 85, and 90. So these last two, 85 and 90% MgO, are really enriched. So the bulk densities are about 180, 185 pounds per cubic foot. These are typical porosities from about 16 to 20%. You can see the cold MORs and the cold crushing strengths are rather good. These are 1,000 to 1,500 MOR in PSI, and the cold crushing, these are around 8,000. This is about 5,000. And the hot strength is rather good. These are 2,300 F. These are over 2,000. And even at 2,500 at 2,500 degrees F, it's still about 670 PSI. So the MgO contents have to be the same as the grade of MgO. And the balance is primarily alumina. And you'll have CaO, Fe2O3, and SiO2 as some of the impurities. So that's the last slide. So we did chrome magnesite, phosphorite, and spinel. So that's what I have on the finishes up the basic refractories. Wednesday, we'll start on zircon and zirconia-based refractories. And again, if you have any questions, just let me know. And thanks for listening. And I'll see you on Wednesday. Thanks again.